Okay, guys, so I'm going to go ahead and do a video on starting some material from Chapter 8. So I know this is coming before I'm doing the review for Exam 2 and talking about the exam format. That video will be coming as soon as I get some things finalized, but since it's kind of quiet around my house right now, I thought I would just go ahead and start talking about some of this material, which will be on Exam 3 in the final. So what I want to, I guess, talk about here with this chapter, which this is probably the longest chapter in Organic 1, is addition reactions. And what we're really specifically talking about is additions into alkenes and alkynes. Now, I've changed the settings on the camera, so things may look a little bit washed out, but I think it makes the colors stand out a little bit better here with this. So I apologize if there's any washout that you're noticing, but I think this is a little bit easier to view. Okay, so what this section really entails is I'm going to go over an overview reaction with you guys as to how these generally work. So one of the things that is a good idea to get into a habit of doing is starting to number your carbon systems if you haven't been doing that already. This is very important going forward, particularly in the next course, because you don't want to lose or gain any extra carbons. Now, one of the things we can say about this system is this pi bond here, this is considered to be electron rich. So that means it has excess electron density and is somewhat reactive. Now, what it's going to react with is generally something that is positively charged, what I'm going to call E+. Now, this particular species is something that is electron poor. That's why it's positively charged. And it doesn't necessarily have to be positively charged. It just has to have positive character. These are what are known as electrophiles. Okay, so the direction of the arrows here for the arrow pushing is that, okay, the pi electrons go and add the electrophile. So when this happens, redrawing our system, you really have one of two places that you could add that electrophile. So here I'm putting the electrophile on carbon number 1. So there's 1, 2, 3, 4. So if you put an electrophile on carbon number 1, well, then that means you have to put a positive charge on carbon number 2, okay? Because now there's no longer a double bond there. The other option, okay, is, well, if you were to, say, add the electrophile at carbon number 2. Okay, I'm going to blow this up a little bit. Try to. There we go. Okay. And so here the positive charge is on number 1. Now what you want to be asking yourself is, okay, if you had to choose which one of these two is more likely to occur, so which is preferred in this situation? Well, the answer is well, it should be this one up here. Now, the reason why is because, well, your carbocation is more substituted, so it has a lower energy of activation that it travels through via the Heyman postulate. Whatever the intermediate energy is, that's what the transition state is going to most closely mirror. And so that means that this will be predominantly the species that is formed. So remember, carbocations are more stable the more substituted. They are. And this is a very important and, rearrangements are possible. And rearrangements are possible to more stable cations. So we have to keep that in the back of our mind while we're doing this. Now, the other thing I want to introduce here is the term that's used quite a bit in this chapter, which is the word regioselective. So I want to just mention that now. So what regioselective means is preference of bond making, or breaking. Preference of bond making or breaking over all other possibilities. So it means there's a particular region that is favored. Okay, so it's kind of like up here, this was regioselective for carbon 1 over carbon 2 because you got a more stable carbocation. So there's always some type of rationale as to the regioselectivity. Okay, so as we do these addition reactions, I'm going to number them. Okay, so this is the first one. So this is addition of hydrogen halides. Addition of hydrogen halides, which is abbreviated as HX. Okay. Now, if I look at this compound again in a little bit more detail, this time I'm going to go ahead and draw out all the hydrogens in this alkene. Okay. I'm going to keep my numbering consistent. So this is number 1, this is number 2, number 3, and number 4. Okay. If I were to add to this alkene compound HX, okay, then the way I would push arrows would be, okay, this is going to grab that hydrogen. Again, that is your electrophile here. It's adding it in. This is a polarized bond here. And then those electrons are going to go onto the halogen, giving you X minus. And so we've already talked about what the preferential species is going to be, which is going to be that you're going to be adding the halogen, or excuse me, adding the hydrogen on carbon number 1. Okay, and we still have 2 hydrogen atoms here on carbon number 1 as well. Now on carbon number 2, we only have the 1 hydrogen. We now have a positive charge right there. Okay. Now, following this is going to be our halide, which can attack that positive charge. So you ultimately end up putting the halogen here and the hydrogen here. Again, showing those other hydrogens that are present, that were present originally. Okay, now this is an example of what is known as Markovnikov's rule. So I'm going to spell that out. So Markovnikov's rule, okay, which will henceforth I will refer to as Mark's rule, basically states that you add hydrogens, in hydrogen halide additions to the side of the alkene that has the most number of hydrogens. You add hydrogens and hydrogen halide additions to the side of the double bond as the most number of hydrogens. Now, Markovnikov was a Russian scientist that lived in the 1800s, and they did not understand this idea about carbocations, which we do now. So the modern statement of Markovnikov's rule is really to get the most substituted carbocation. Okay, and so this ties back into that idea about regioselectivity. And so if you look at this, and between the two different sides of the double bond, there was only one hydrogen here, and here there were two. And in the final product, there's now three, so that means I've added hydrogen to the side that had more, and the halide goes on the other carbon. So this is a kind of a shortcut to applying hydrogen halide additions, but it's important that you understand, why this works. Okay, now if I were to graph this whole thing out in terms of a one of these reaction profile diagrams, which I want to show what that looks like. So that means we're going to have a axis like this, or a little plane. So we're going to have our energy here. This will be our reaction pathway. Okay, so we're starting off life here as our alkene. Well, focus. Just lost the focus here, guys. So a little bit of technical difficulties here right now. There we go. All right. That was scary for a minute. I apologize for that. Okay. I have to be a little bit careful when I'm doing this now. All right. So now your intermediate that you're going to produce when you add your hydrogen halide to this is obviously going to be higher in energy. That's going to be our carbocation, and that's going to be up here, okay, at this position, where we've added our hydrogen to the side of the double bond that had the most number of hydrogens, and that's where our carbocation is going to be. Okay, so this is going to undergo a reaction that's going to be uphill. You're going to go through this transition state, which is going to most closely mirror this particular intermediate, which I'll label I as the intermediate. Okay, so this is your first activation energy here, E sub A1. All right, now this is actually a two-step process, because once this carbocation forms, well, then the halide is going to want to add into that positive charge. So you actually have a second reaction that occurs before you make your way down here to products. All right. Where now you have your hydrogen that you have added here, and your halogen you have added at this position. And this is where we have our second transition state. So this is our energy of activation 2. Okay, so this is for transition state number 2, and this over here is for transition state number 1. Okay, Now, you'll notice that I drew this a little bit lower in energy than what we started with, and that's generally the case with these, is that since you are forming now sigma bonds in the place of pi bonds, those are generally exothermic processes. In other words, they release energy. And so your overall reaction is exothermic. Now, what's important about this is to note is that it is the first step that is larger, okay, in this process, the larger activation barrier to form the carbocation. So this is really the rate determining step of this process. Now, a couple of things I want to say about this product right here that we've just formed, okay, and that is a question about its stereochemistry, which is the product chiral? Is the product chiral that we have produced? So this product right here. And the answer is most certainly yes, it is. Okay. Yes, as we have a stereocenter. Okay. There's a stereocenter right here. So we have 4 different things that this is attached to. So if you ask what is the stereochemistry, well, the stereochemistry is this is a racemic mixture. Okay, and if you remember what that means that, okay, you have a 50-50 mixture of these 2 enantiomers. Okay, now each one of those is individually chiral, but these are going to have a 0-degree rotation, as you know, half of them are rotating plus, half of them are rotating minus. So there is, in this particular reaction, if you do generate a stereocenter at the position that you are adding in your halogen, that position is going to be racemized. So a statement is if a stereocenter is generated, in an addition reaction, that stereocenter will be racemized. Okay. So that means if we look at a real life example where if we were going to take this alkene and we were going to treat that with HCl, that would end up giving me this compound where if I add hydrogen to the side of the double bond that has the most number of hydrogens going here. Obviously there's an understood other 2 hydrogens right there. And that the chlorine would be at this position. And this right here is going to be a racemic mixture. And since there's only one stereocenter, okay, that means these are enantiomers of each other. So I've shown the plus minus to indicate that this is a racemic mixture. And if you were doing a distillation of these or chromatography experiment, this would come down as 1 fraction, as they would have identical properties. Now, a warning about all of this. Be careful. Be careful. If the alkene already has a stereocenter, before the addition reaction, an alkene already has a stereocenter before the addition reaction, its configuration will remain unchanged. Okay, meaning that stereocenter will remain fixed. Okay, and so if you were to generate a new stereocenter, well, then that stereocenter would be racemized, but the other one would stay the same, and that affects the nature of the two products that are produced. So, in other words, if we had, say, an alkene that looked like this, where I have a fluoride that is clearly coming towards us, wedged. Okay, this has R, it would be assigned as an R stereocenter. Okay, now if you were to treat this with HCl now, that would do our Markovnikov addition. Meaning you would add hydrogen here to the side of the double bond. Line number 2, line number 2. And you would have a positive charge here, but this fluoride over here, it is still there. It has not moved. So now when the chloride comes in to attack this, you really have two options here. The fluoride could attack the carbocation from the bottom. Okay. At which point you would see a isomer that would look something like this. And that happens to have R stereochemistry. But if the chloride were to attack, let's say, from the top face above that carbocation, and add into that, well, again, your fluoride would remain unchanged, but now your chloride that you've added in is now going to be wedged up as well. And so this is going to be RS configuration. Okay, now the question about this is, okay, what is the nature of these two compounds right here? Okay, and so questions you'll often see asked about this is how many fractions can be distilled off as products? How many fractions can be distilled off as products? Now, in the previous question that we just looked at, okay, since we were producing this racemic mixture, okay, that's going to come off as one fraction because those are two enantiomers of each other. So the question you have to ask yourself is, well, what is the nature of these two compounds right here? And the answer is those two compounds are in fact diastereomers of each other, which means they are not mirror images of each other. And so if they had been mirror images of each other, well, then these configurations would have changed down here, okay? And so only this one changed, but that one remained the same. So that means these are not mirror images of each other, but are configurational isomers. And as you remember, diastereomers have different physical properties. So that means you would expect to see two fractions, okay, that would come off in distillation or chromatography as diastereomers have different physical properties. Meaning they have different boiling points, they have different elution rates, and so those can be separated, okay, using normal techniques. Now, the one other thing I want to mention here, I guess in closing about this, is just some examples of rearrangements with hydrogen halide additions. Okay, so example is, well, what if we had, say, this six-membered ring, and we wanted to add HCl to this. All right. If we were to apply Markovnikov's rule, okay, as stated, so this is going to do a Markovnikov addition, where you would expect to put that hydrogen there, either carbon 1 or carbon 2, you would expect to put the hydrogen atom on carbon number 1. And that's because you end up putting a positive charge right here on a more substituted carbon. Now, this carbocation is secondary, okay? And the thing to look out for is that, in fact, there is a hydrogen atom right here, okay, that is on an adjacent carbon that is more substituted. And as we saw in the last chapter, that is when it is likely to get a rearrangement, in this case, a 1,2 hydride shift, meaning hydrogen and electrons and all move over to that new position, okay? Now, that is going to give us this carbocation now, which is going to be on this position, as that hydrogen atom will have moved over to here. And now that is a tertiary carbocation. So the chloride can, in fact, add into that position. Giving us this product, okay? So that would be the major product that you would see there. Now, these can get really, really bad, okay, some of these problems. And so one of the things that I want to, I guess, kind of set up here and have you guys think about, and the answer to this is in the notes packet that is posted on Tracks. So you can go in there and look at that. But I want you to kind of think about this first, is in this particular problem, okay, and I'm getting ready to show you that this system, if you were to add HCl to this compound, it turns out that there are actually 4 different products that are produced at a minimum that come from ring expansion. Okay, so 4 possible ring expansion products. Okay, and there are other possibilities as well. You could shift the methyl group but here I'm talking about the ring expansion product. So I guess what I'd like you guys to do is to try to see if you could figure out and determine what those 4 different products are and what their relationships are to each other. Okay, and so the answer to that is on page 4 of the notes posted on Tracks. And so that may be a good exercise for you to try to do that one and then go and check and see if you're coming up with the right conclusion. Take your time while doing it. That is a fairly evolved question, but it is one definitely worth practicing. Okay. Now, I know this video is dragging on a bit, okay, and so I think what I'm going to do here is I'm going to go ahead and turn the camera back around. There we go. Okay, so there were some editing issues. I don't know if I'm going to be able to edit everything out, so I apologize for the long pauses and the focusing issues there with that. But this is a very important concept of this Markovnikov addition. We see this used a lot in chemistry, and every organic chemist knows what you're talking about when you're talking about our Markovnikov addition. And basically, it just means adding hydrogen to the side of the double bond that has the most number of hydrogens. And the reason is because you get a more stable intermediate that is produced as a result of that. Okay, so every other addition reaction that we're going to do from this point on, I'm going to be building on that key premise, is thinking about what the intermediate is that we're producing from that process. So there are several more addition reactions coming after this one. And each one of these, I will talk about their specific regiochemistry, as well as something called their stereoselectivity, which that word should kind of make sense to you what I'm talking about there as it relates to their stereochemistry. So we will get into that in the next video, and hopefully I'll have another couple of videos posted on Chapter 8 here pretty soon. And like I said, you can expect a video coming to go over how we're going to do the exam next week and the format for that, as well as a review over some key topics that you should be going over. Okay, so I hope everybody's doing okay. Everyone take care, and I will talk to you again soon. Okay, bye-bye.